Now, last week we looked at the zeta and omega n parameters, which were defining us a second-order transfer function. And we have spent some time on it because it's quite important for control system design. This week, we will be building up towards the more complicated controller design. And one of the things that we learned today is going to be the zeta and overshoot relation here, which is basically most of the time given in reverse, but I've turned it into a relation that will be more suitable for some requirements. And we have a certain second-order system to begin with. We are going to design some controllers, the P, PD, and PI controllers. But this week's controller design is not going to be optimal, and I will not recommend you to design the controllers the way that I'm going to design them today. Because I want to introduce you to these controllers, it's not going to be the best way of designing them. And you can see we have a second-order transfer function to begin with, which has already a zeta and omega n value on its own. Don't mix them up with the closed loop requirements because they are basically different from each other. A system can have two poles, and for all pole pairs, we can come up with zeta and omega n values. That doesn't mean that this is going to be the specification of the closed loop, so that's going to be a different topic. But what I'm trying to demonstrate here basically is going to be that you might have a certain zeta and omega n value for your system. Then you might design a different controller. And in the closed loop, you will end up in a different zeta and omega n setup. So that kind of demonstrates you that we are trying to change the behavior of a system by tuning zeta and omega n. Because our formulas relate to zeta and omega n, this is the way of the change in behavior that we can express. So that is going to be it for this zeta and omega n here, and we will end up in different zeta and omega n values for almost all controllers, I guess. So again, let me repeat, I'm going to design them in a more introductory way. It's not going to be the final way of designing PD and PI controllers. Yeah, let's dive in with the P-type controller design. But now today's requirement is to have 10% overshoot in the closed loop step response. We had the settling time version of this, and we've designed for that, but now we are looking at overshoot. And from the formula, I'm denoting log E, which is natural log, by the way, but I needed to write this down explicitly, since when you're using a calculator, you might want to just look for the natural log. But when you're coding in MATLAB, that's not going to be the case. You're just going to use log, because log 10 and log 2 are the functions in MATLAB that we use for 10 base or 2 base log. So if you write down log 10, log 2, these are the bases. But if you write down log, it's just going to be the natural log that we're looking for. So overshoot is 10%. And we're looking for a certain zeta value because they directly relate to each other. So minus log overshoot divided by the square root of pi squared plus log overshoot squared. Now, this is a nice relation because you can see that they directly relate to each other. And we've talked about this previously, because if zeta is equal to 0, we had this pendulum. There was no friction. It would just go on and on and on infinitely. That would correspond to 100% overshoot, for example. If zeta is equal to 1, that should be 0% overshoot. Then there is basically this relation which kind of models the zeta, the correspondence between zeta and overshoot is going to be basically this. Yeah, you can directly come up with a zeta value. That's quite nice, if you ask me, because the settling time formula doesn't give us the same thing. It just gives us a multiplication, or the real part of our poles. So Now, let's move on to our p-type controller design, because that's going to be the easiest one. I have to define my system before that. So it's going to be zeta 1 and omega n 2. So let's have zeta equals 1, omega n equals 2. The transfer function is going to be omega n squared, and then 1, 2 times zeta omega n, and omega n squared again. I'm going to define the symbolic version 2, because that's going to be necessary in a moment. So omega n squared divided by s squared plus 2 times zeta times omega n times s plus omega n squared. There we go. Yeah. Now, how do we design a controller when we have a p-type controller and the requirement of 10% overshoot? Well, nothing actually changes here. We are going to use basically the definition of our controller, which is going to be k. So the controller itself is going to be equal to a certain number. And then we have the closed loop, which is FSS times TSS, and then this whole thing 1 plus FSS times TSS. So this is our closed loop structure. Then we can divide this into its zero and characteristic polynomial using nomdan, TSS. Then we have basically PCS. So let's run this. You can see s squared plus 4s plus 4k plus 4. We could also do something like this. TSS equals simplify, and then fraction, and TSS, and then maybe pretty TSS in order to show the transfer function itself. And you can see this is going to be the transfer function, 4k divided by s squared plus 4s plus 4k plus 4. You don't really have to take this route in terms of calculation of the closed loop, because you can also divide the transfer function, the open loop transfer function, into its numerator and denominator, and then ns times k plus ds will give you basically the same characteristic polynomial. But of course, you then have to calculate the zero polynomial for the upcoming controllers. Here, for the p-type controller, it's not going to be that big of a deal. So, as the characteristic polynomial implies, we have a second-order polynomial. And therefore, we also have the zeta value here. What we can do is we can just define a omega n value here, omega n real, and we can form our desired polynomial, which is going to be s squared plus 2 times zeta times omega n times s plus omega n squared. Now, the nice thing about this system is that we don't really need to define a residue polynomial here, because the orders are equal to each other. So we have PDS and PCS, and they are both second order polynomials. So what left is basically to define the actual problem, where we take the coefficients of the characteristic polynomial and the coefficients of PDS, since we want to see what they look like. Start from 1 up to length problem, display using VPA, problem I, and there we go. So this is basically the closed loop transfer function. This is going to be the set of equations that we need to solve. Since both PCS and PDS have the highest order term coefficient 1, we have this 1 equals 1 trivial equation. It is necessary to have this, but on its own, it's not contributing to the solution. And other than that, we can see that omega n can be directly calculated by dividing 4 into 1.182. Once we have that, we can plug in omega n squared here, extract 4, divide it into 4, and we get k. So basically, we can learn from this the fact that we can calculate only one possible omega n value, and there's just going to be one controller that satisfies this overshoot criteria. Or in other words, our root locus intersects with the zeta line just once and for a specific omega n value and k value. So Therefore, what we can do, we can ask MATLAB for the solution of the problem. And I guess the solution is going to be symmetric due to omega n squared. Let's see. Well, it's not actually, because this is directly a value. So therefore, we have just one value here. So let's have k val equals double sol dot k, and omega n val is going to be omega n. Once we have that, we can define our controller, which is going to be k val. And from this point on, we can create a figure and actually a subplot, maybe side by side, to have basically the step response on one of them. So x label is going to be time, then y label is going to be yt, and then the title is going to be step response. And then maybe show the legend, and ax1 equals GCA. For the second one, we might want to just create a hold on, and then nothing else actually, x2, because I'm going to draw a root locus on that. So since we have fs, we can calculate what ts is going to be. That's going to be feedback, and then fs times ds comma 1. Once we have that, we can just directly obtain the step response here. Step ts, plot ax1 t comma y, maybe blue with line with 2, and maybe display name, so that we get basically the settling time and stuff shown. String TSC plus OSE plus string OSE plus percentage, something like that. For that, we need to extract the step info of TS, and then TSC is going to be info.settling time. And then OSE is going to be info.overshoot. And yeah, that's kind of it. Now, on the second plot, we will have our locus of GS on the second axis. Well, since we have a closed loop setup, since we are designing a p-type controller, what we ideally would like to see is our closed loop pole zero spread. So we can basically place the root locus and then place the pole zero on top of this root locus plot. So C poles and C zeros is going to be equal to PZ map, so that I get basically what the poles and zeros in the closed loop are. And I'm going to plot them AX2, the real values of the poles, the real values of the actually imaginary value of the poles, and then something like this, line with 2, blue, and then the same goes for the zeros, of course. Then that's going to be BO, and one final thing could be the S-grid here. We've learned this command last week, where we provide basically a zeta value and possibly an omega n val, so that we kind of get these zeta lines and the omega n square, actually omega n circles. So if they intersect, those are going to be our closed loop desired poles. So it seems like we can just run this now. And yeah, of course, that's not right. There we go. Now, of course, the zoom level here on the root locus plot is not satisfying at all. And the omega n value itself was 3.38. So I can just directly change the x limits on AX2 to my preference, like -4 and 0.5. You can also do this for the y limit here, so that we zoom out a little bit or focus on the basic stuff here. So, yeah. We might want to give it a 2.5 seconds of a settling time here. 2.5. Yeah, that should be perfect. Now, first of all, we observe that we have poles at -2. And since omega n was basically equal to 2 and zeta was equal to 1, we have coinciding poles on top of each other here. And due to the lack of a finite zero, the asymptotes became 90 degrees and negative 90 degrees. Therefore, we go up for one and down for the other. And we can see that our zeta line passes through this horizontal line here, where we have basically an intersection of omega n and zeta. We didn't know which omega n value this was, but we know that if we have 0.591 as the zeta value, we will have a fixed angle for this line, and they will eventually intersect because this goes to j infinity and minus j infinity. So they will basically have an intersection here. And this exactly happens where we have 3.38 as the omega n value. And we can see that the overshoot value is exactly 10%, which is nice because the zeta and overshoot relation seems to be working pretty well. But on the other hand, we know what zeta is, we know what omega n is. What we can do is we can look for the settling time value. That would be 4 divided by zeta times omega n val. And that doesn't really work that well in terms of accuracy. You can see 1.7515 is kind of the value that we get here, but theoretically, or according to the settling time model, we should have 2 seconds of settling time in the closed loop. That's not that of a big deal for the settling time, because first of all, last week we've learned that it is 3.91 for a first order system and something around 3.8489, something like that for a second order system. But yeah, we will use it as 4, and that's okay with us because it's still going to be a bit different than its self. And we've seen that actually that there's a nonlinear behavior around zeta 1 and maybe 0.8, 0.7, something like that. So that's probably the reason why we have this difference here. So the settling time formula is not that accurate, but it works because it's giving us the inverse relationship between the settling time or the speed of a step response and the system poles. So that's enough for us with this accuracy. Sometimes it works well, sometimes it just has a little bit of an offset. But for overshoot, that's working way better than expected, actually. And yeah, what we can observe from this is that there's just one solution. And theoretically speaking, we can see that in the closed loop, we will have always the same real value, which is basically -2. So it will not change no matter what. It will have the real value -2. If that's the case, theoretically, the settling time of the closed loop can never change. It's just going to be equal to 2 for all the closed loop controllers and their step responses, of course. Now, we could just change the k value a little bit. But before I do that, another thing that we can observe from this is that even if we apply 1 unit of input to the system in closed loop, the resulting steady state value here is not exactly equal to 1. So we have a bit difference here. And if we want to showcase that there's a quite difference here, what we can do is we can come up here, plot x1 t comma 1's size t, and then a lagged line for the reference itself. We can also assign it a display name called reference. So if we run it again, we can see that the references here equal to up here equal to 1, but our steady state value is quite far away from that. So this is called the steady state error because there is a difference in steady state. After the settling time or after 2 seconds, we are in a steady state condition. Therefore, this will remain the same. And we can also see why this happens because the p-type controller in the closed loop ends up being this transfer function here. And if you use the final value theorem, you can see that you should multiply this with s. And here we would have 1 divided by s because unit step input. And then they will cancel each other out. Limit s tends to 0. This term goes away. And we have 4k divided by 4k plus 4. Or you could say that k plus k divided by k plus 1 is basically the steady state value. Since we know what k-val is, we can see that k-val divided by k-val plus 1 gives us 0.65. And if you measure this here, you basically get the same results. Eventually, this will settle down to 0.6505. So 1 unit of input, 65% of its value is going to be the value that we are at. So if this is kind of a control system that we care about in terms of reference tracking, then it's not a good controller. We can improve on our controller, and I'm going to do that exactly now, but it will have consequences. One thing is that this system doesn't change in settling time. And since this ratio is 4k or k divided by k plus 1, I could do the following. If I increase the value of my controller k, let's have it twice as big as it is, then I should improve on this resulting thing here. For example, if I choose 3 divided by 4 should give me 0.75. And 4 divided by 5, for example, if k is 4, it should give me 0.8. So if I increase k, this definitely improves in terms of reference tracking. It will be a better and better in terms of steady state error. And its settling time wouldn't definitely change theoretically because it will have still the real value of -2 here. So 4 divided by 2 should give me the settling time that I want. But since I'm on this root locus and since I'm increasing the gain, it means that I would intersect with a different zeta line which will have a greater angle. And due to the cosine relation between zeta and theta here, the zeta value would drop down significantly. Now that would increase my overshoot. So I can improve this in terms of steady state performance, but then I would have to give up on the overshoot requirement. So let's see if that really works. And I can just come up here, multiply with 2. 0.6505 was the result. And you can see it kind of improved, but you can also see the zeta value is totally different. Let me increase it a little bit more, like 4 times. You can see we are kind of reaching 1 and then we are dropping down back here, but we are out of our region basically, and we have even a lower zeta value here. So let me increase it further more. Let's have 10 times here. We're kind of getting there, and our settling time value, as you can see here, is around 2 seconds. So even though the settling time formula is not that good in terms of accuracy, it still works and it can give us the settling time of a system. But you can see I can still increase it, and still it will decrease the steady state error here, but overshoot becomes greater and greater and greater in magnitude. And I can't do anything against that. But the nice thing about this controller is that it doesn't matter how big the controller gain gets, it will never become unstable because, well, we're far away from the j omega axis. It doesn't change angle. We're on the asymptote, and we will just go up and on, up and up, and it will just increase the damped frequency of our pole pair. It will decrease the zeta value, increase the overshoot, but it will stay on this line, and that will just fix the settling time. But yeah, at least we're not, we don't have to handle instability in this case. So I can just keep increasing like 100 times, for example, and then run it. And you can see, yeah, of course, we have kind of the settling time that we want here, 1.86 in this case, for example, around 2 seconds. But then again, we have 80% overshoot. And yeah, this as a step response doesn't seem to be the best. But you can see the steady state value here becomes, in terms of steady state error, becomes irrelevant at some point. You're just messing up the whole system response. I wouldn't really care about this system because this is too much overshoot, too low of a zeta value. But yeah, it is what it is. So we can mess up like that, or we can just live happily with our result and do nothing to it, because this is a much cleaner way of doing it. Now, there's an open loop strategy where we can fix this gain and have reference tracking, sort of, but it's not the best. Now, since we apply 1 unit of input, and we know that it would be kval divided by kval plus 1, 0.65, what we can do is we can invert this ratio, apply that as a step, and then fix this steady state value so that it becomes equal to 1. So what I mean by that is there is a direct relation, it's proportional. So I can just calculate what I exactly need for as an input in order to have a 65% in the output. So I should increase that accordingly. So that would be basically the inverse here. So let me just take the inverse. And it shows that 1.5372 should be applied to the system. So let me just apply that to the system. Note that I'm applying this to the closed loop here. And this means that instead of applying 1 unit of input, I'm applying 1.5372 units of input so that I'll get basically reference tracking. And this is not, again, perfect, and you can see that here. I need to work with the accuracy a little bit more, maybe increase it, maybe decrease it a little bit, so that I match exactly the value 1 here. And in fact, the last value of our step response is 0.9917. It seems like we're almost there, but not exactly. And you can see that this is, again, still a problem because I'm just adjusting my gain in terms of input. But that wouldn't correspond to anything in real life, because you would have disturbance and noise and stuff like that, and you would never match the reference in terms of reference tracking, because this is kind of an open loop strategy. It's not taking into account that the output has dropped. I'm just coming up with a magic number in order to fix the ratio between input and output, which is basically open loop and not closed loop. And we'll see at the end of the day what closed loop would look like. So now this is the p-type controller, and this is the best I can do with this system. And let me remove this ratio here, because it doesn't really make sense if you're working with a p-type controller. This is what it is at the end of the day, and this is the closed loop control performance of this. Improving this with open loop stuff doesn't seem to be realistic to me. But yeah, still knowing it is important. So this is the best we can do with a p-type controller, and we don't have reference tracking here. We have an overshoot value that was expected from us, and we gave it, and this is basically the result. Now, this is a introductory lesson in terms of controllers. Therefore, we will not force this controller to have other specifications, because we've already given the specification only to be 10% overshoot, and that's it. There's nowhere around here written down that it should have a reference tracking. I'm just adding that as a comment to the controller, because yeah, that's almost always going to be the case for a p-type controller. You will never have a zero steady state error in terms of step type inputs reference tracking, because p-type controller is not capable of doing that. Maybe the system on its own is already capable, then the p-type controller can just contribute to it. We'll see, we'll talk about this later today. So this is the p-type controller, and this is the way we design this. So there's no issue at all here. But what can we do in terms of controller structure? What can we do differently to get a different result, or a PD controller, for example? Or what is a PD controller? So I'm just going to get to this point, comment everything out, and let's see. Well, we can see, for example, looking at the root locus, that, well, the root locus is just going straight up and down, and that's basically it, because the system has just 2 poles which coincide on -2, and that's it. But we can actually do something like adding a 0 to this root locus. And the reason why I'm first going to add a 0 is that we know that from the root locus plotting rules, at least, we know that each pole tends to a 0 from the open loop. So an open loop pole will tend to an open loop 0. Since we don't have any here, we can add one on our own. So we might want to add something on the left because of last week's discussion, where we've seen that adding it somewhere around here in the dominant region messes up the whole step response here. Especially a 0 is dangerous in terms of adding it in the dominant region. We might want to add it away from the dominant region, so in the non-dominant region, basically. So 4 times, 5 times away here. So at 8, for example, at 10, we might want to add a 0. So a 0, since one of the branches or one of the poles will tend to it, and since it's going to be symmetric, these 2 branches will basically bend towards left, towards our 0, and we will end up in a different root locus scenario. So basically, if we are not happy with our root locus, maybe we want to add a 0 to bend it, to change it, to alter it, and then work with the resulting root locus plot. So that's kind of why we are looking towards a PD controller, because it has just 1 0, and then it looks at this new root locus and kind of chooses the p-type controller. So, and the way of defining that would be, in terms of a transfer function, would be s plus z. So I'm just going to add another parameter here. So this is going to be my PD controller, or my new control strategy. I'm going to add a 0 to the system, to somewhere on the left. It will bend towards it, and we would then choose a p-type controller accordingly, and hopefully that will solve our issues. Now, why would we add a 0, and especially why to its left? Well, due to the dominant pole placement strategy, we want the 0s and residue poles to be away from the actual poles that are shown here. So we have this pole pair, this should be dominant, and everything else should be out of the dominant region. So that's one thing. But the other thing is that we know that if the real value is small in terms of magnitude, then the system is going to be slow. But if we bend this towards the left, we will end up in higher magnitude real values. And that would increase the speed of our system, hopefully and probably. It's not going to be for all setups, because, well, we might enter with a 0 in the dominant region. But other than that, if we bend it towards left, we would have greater values, like, for example, -4 here instead of -2. Then we would increase or decrease the setting time. We would halve it, so it would be twice as fast as this setup here. So we could speed it up with a PD controller. So how can we call this controller a PD controller, where we only add a 0 and a p-type controller on its own? Well, if you just do the math here, you will end up in k times s plus k times z here. And due to the Laplace transform, you can see that k times something derivative, and we know that the input is going to be the error. So this is dE dt plus k times z times e. So basically, this is the proportional part, this is the derivative part. Therefore, we call it proportional derivative controller, or PD controller in short. So that's basically the explanation why we call this a PD controller. PD because we have KD times S plus KP. And this is the derivative part, this is the proportional part. Of course, you might have expected it a bit differently, but that's not the case. K times Z here corresponds to the proportional part, and K here is directly the derivative part here because of the multiplication here. We could, of course, change that, but that's not the topic here. And when we're designing a controller, it matters which method we use, because if we use the root locus method, we will automatically stick to this notation here because of the angle condition, and we want to satisfy the angle condition. Therefore, we will directly calculate the angle contribution of a possible zero. We will add the zero, and then we will look for the gain condition. So we will be forced to use this notation here. But when we are using the algebraic method, which is the case here in MATLAB, where we use the polynomials, we should favor this representation here because it is a linear polynomial. So linear in terms of a polynomial is important because the problem will end up being a linear problem. And that's very important if you're in an exam. If you're on a time limit, you would rather stick to a linear problem than a nonlinear one where you have K times Z already on its own, which is a nonlinear term, and you wouldn't like to have that. But I'm not going to do this for this week and this week only. And I'm going to define my problem like in line 16, whereas I should define it like KD times S plus KP. But since I'm introducing stuff here, I'm not going to do that. But please note that this is not the way that we should design controllers if we're using the algebraic method. But for this week, I'm going to do it anyways. So the only thing that we should do in terms of the algebraic method is just go along with the structure and do the same stuff over and over again. So it's not going to be a big struggle in terms of coding here because we don't change anything. We're just going to get the closed loop transfer function, and then we will define our problem, and hopefully MATLAB will solve it. So that's kind of the strategy that we're looking at here. Since I'm at it, before I forget it, there we go. So this is run one. Now, if we run the PD controller design problem, we get this closed loop transfer function. Now we can see that it looks a bit different because this was the line of our previous problem where we directly calculated a certain omega n value, then we transitioned into K. But here, we cannot do that basically because of the fact that we have K, Z, and omega n as unknowns, whereas two equations are basically relevant to us. So two equations, three unknowns, infinite amount of solutions. So we can basically do anything we want here. Or in other words, we could actually decide on the overshoot of the system and on the settling time of the system, or rise time or peak time, or whichever you pick. So we can basically design only a controller for zeta if the controller is a p-type controller. But in this case, the PD-type controller introduces one more parameter. And due to that parameter, we're able to have multiple choices, actually infinite choices. And we could actually come up with two specifications for the same system by changing the overshoot and another time domain specification like settling time. Because this one gives us, the overshoot gives us the zeta value. What we can do is we can just transition into the omega n value because we could fix settling time, which is 4 divided by zeta times omega n. So omega n is going to be the unknown. We can solve that if we have a fixed settling time. So zeta and omega n can be both manipulated with a PD controller simultaneously, whereas p-type controller can just manipulate one of them. So that's nice. We have an additional parameter, and that helps us out. But of course, there's this danger where we can enter, or where the zero could be in the dominant region, and that would mess up stuff. So with that restriction, of course. Now, I'm not going to choose anything here, and it's not going to be optimal. I'm just going to leave it to MATLAB, which is a bad idea. but I'm going to go with it for this one because it's just demonstrative. So let's do it. Let's try to solve this problem using MATLAB. It will give us an arbitrary solution. And in fact, it gives us multiple solutions. Sol dot omega n and stuff like that. So let me just convert everything into double and look if we have something that we can work with. So we have k omega n and z. K omega n and z. So what we can do is we can do the following. Omega n val by definition needs to be positive, or at least equal to 0, but positive. Therefore, we could eliminate this solution here. But other than that, we will have different omega n values, but also, of course, different k values here, negative or positive, doesn't matter. But there are only two distinct or two unique z values here that MATLAB came up with. Of course, this is not ideal. We could place the 0 at the origin, and we could move it along the real axis as we wish, and each of them would be our solution, our candidate solution. So there are infinitely amount of solutions, but I'm just going to demonstrate with different setups here, and MATLAB comes up with some nice examples, and I'm going to use them directly. But other than that, we should optimize on that. Maybe we should choose the settling time, etc., in order to come up with a unique solution. Or we could use this freedom in order to optimize stuff, but that's going to be in the upcoming weeks. But for now, we're just going to look for a solution, a random solution. So let me just define the index, which gets rid of the negative omega n values here. So k val is going to be k val index omega n z. So omega n val, z val, and z val. So let's also bring this up here. Nothing changes really. But what I want to do now is, since I'm going to have multiple solutions, I just want to choose I equals 1, one of them, based on k val, that's going to be I. And this is going to be the closed loop. I'm going to calculate the step response, step info, settling time. Oh, nothing is going to change. I could leave the reference out here, and then we would have this. Now here, note that we have negative and positive values for the root locus. What I can directly do is I could check upon the positivity or negativity of k val that I'm looking at now. If it's positive, use this root locus. Otherwise, use a different one, which is going to be basically only negative, nothing else. And Poisson map, plotting of them, S-grid, they should maybe stay. X limit, I'm not sure. Omega n val seems to be right. Yeah. Let's do 4i from 1 to 3 like this. Now, what happens if I run this? Let me see. So we end up in this. Of course, changing the colors might help us out a little bit. So I'm going to assign some colors here. So colors equal to maybe red, maybe blue, maybe magenta, stuff like that. So this is going to be colors I. I'm going to place this. Let me also give it to the root locus plot here so that it changes color, basically. There we go. And then, of course, erase these here. Just give the markers. And then the color. And yeah, that should be it. Now, we could also give it a maybe 8 seconds of simulation time here to have them look similar. So there we go, actually. Yeah, but we still have an issue here. you can see that the root locus plot is not actually correct at all, because it doesn't have the zero. It doesn't show the zero because I'm not plotting the right one. If we have a controller other than a p-type controller, for example, if we have added a 0 to it, and if the forward loop looks like this, or if the whole feedback structure looks like this, then it is important to actually include all the dynamic parts into the transfer function and then look for the p-type controller. Because when we are designing a PD controller, for example, or a controller that consists of a p-type controller and dynamic stuff, we should add the dynamic stuff to the open loop transfer function and then look at the root locus plot, because the root locus transfer function or the root locus equation looks like this. And k is just going to be a parameter. So in that case, the g that we should look at should be corresponding to s plus z times gs, not gs on its own. For this reason, we need to basically take this part where the transfer function itself is also not right. I didn't also change that one here. Let me update that too, because it should be z val I, and I should take this dynamic part, add it to the transfer function whenever I'm plotting a root locus. So this looks more like it. Run 2. There we go. Now, one nice thing that we did is that we've shown the setting times and overshoot values here, and we gave matching colors. So, first of all, when we place the 0 near the origin, and that would be, I don't know, exactly at 0.1, it's quite near the origin here. You can see that it kind of creates an attraction to itself, so that the root locus is kind of bent towards itself. This kind of this setup is kind of an interesting one, because, well, we don't want to slow down the system that much, and when we add the 0 as the dominant part here, well, that's not making sense in terms of dominant pole placement, because now it doesn't make sense to have this zeta value and then have this omega n value, because the 0 on its own is dominant anyway. So yeah, I don't really care about the pole pair anymore, because this will dominate the behavior. And you can see it doesn't seem like a usual step response setup. It has an overshoot, a very high overshoot. But since we are on the negative root locus and k-val, the corresponding k-val here, line 2, is negative, this one here, we have also a change of direction. Instead of going up to 1, we're just going down to -1, and we have just an interesting step response, which we wouldn't rather have. So it seems like adding the 0 near the origin, since it will create an attraction towards itself, doesn't really make sense, because 1, we slow down the whole system. 2, the 0 on its own is dominant, and 3, we're on the negative root locus. We have a negative coefficient. So this is not a good control design in terms of dominant pole placement and the stuff that we want to do here in terms of overshoot and etc. And you can see that the overshoot value is just out of its mind. The shape is out of its mind. We want to track, for example, the step response. That doesn't do anything like that. So it's an awful response, and we don't really want to have that. But we can see that 1,0 value that MATLAB came up, which is basically the same value, 11.34 roughly, it kind of creates the same root locus plot. And that's the reason why we see only 2 different colors, because this overlaps with the red one here, because it's basically the same root locus. We've chosen 1,0. But you can see that the zeta line here intersects with this root locus twice. Therefore, we have 2 different solutions. And that's quite interesting. And this is also the reason why I'm using the MATLAB solution here, because it's demonstrating different aspects of the same controller. Now we can see that we have a lower omega n value solution and a higher omega n value solution, which of course also correspond to different settling times because of the real value magnitude of the closed loop poles or pole pairs. The 0 seems to be in a good place, better for the red one, a little bit less better for the magenta one. And yeah, in terms of k-val, we can also see that one of them is a lower value, the other one is a higher value, and still k-val is important, or actually k-val times z-val here is important, because this will be the overall gain. In terms of steady state analysis, we can see that 4kz is going to be constant term of the numerator, and 4kz plus 4 is going to be the denominator. So if k times z increases, the steady state behavior will increase in terms of performance. In terms of reducing the steady state error, it will be a closer one. And you can see that because the last solution here has a higher value in kz, which determines the steady state error here. And the steady state error is way less than the red one solution because the red one has 4.78. So we can see that the magenta one is a better one in terms of steady state response. But then again, its overshoot is a bit higher than the other one because, well, the relative distance of the poles and the 0 is lesser for the magenta one, and it's greater for the red one. So the red one is a more dominant solution. Therefore, our overshoot value is way better for the red one than the magenta one. So there's again a choice between two. We could increase the steady state behavior performance, but then we mess up the dominance ratio, whereas vice versa also holds, where we increase the dominance factor, but then again the overall gain is lower than that, so therefore we have a less better performing steady states. So yeah, and that's also explainable from this root locus, because we hit it before we hit this one here. So this one has more gain than the red one. Higher the gain, the better the steady states. But yeah, these are the three possible out of infinite amount of possible solutions, and we can improve as I've already talked about it. But of course, it has its limit. When the 0 is here, we don't really want to path we don't really want to surpass this limit here, because then the 0 will become dominant. From this point on, this half of the root locus here is not that usable in terms of PD controller, because the 0 will get in our way. It will become dominant as it was for the blue one here. So we have a small range before we hit that, and therefore we need to look for it and try to come up with zeros that are far away and that try to match our requirements. So, well, this is basically the way of designing a PD controller, but this is not the best way of designing a PD controller, as I've talked about earlier. And you can see that the system still didn't improve in terms of reference tracking, but we got some solutions that work better than others, and we can optimize on that. We can see that we might want to just iterate through the possible solutions a little bit. Now, what about the PI controller that we hear about? Let's look at the PI controller and how we define it. So let me just comment out everything again. Now here, interestingly, I'm not going to add anything that is not known. So it will not introduce additional parameters. It will not introduce unknowns, but it will just introduce a divided by S, or an integrator, a pure integrator, or a pole at the origin. And that's it. So it is kind of a PD controller with an extra pole at the origin, and that is called a PI controller. It seems to be a bit different, but this is all it is. And if you examine this a little bit more, if you factor out this, you will see that we divide into S and into S, and this S divided by S will vanish here. So K is going to be the proportional part. But then again, we end up in an integrator part because 1 over S times K times Z is going to be the integral part. So Kp plus Ki divided by S is going to be the transfer function that corresponds to the PI controller. And as you can see, all it does is it's adding a pole at the origin or a pure integrator to the system. And then it adds a 0 hopefully on the left half plane so that it kind of attracts one of the poles. But then again, we're adding 1 pole at the origin. Now, the origin is a dangerous place if you think about it, because, well, in terms of stability, we can mess it up. And we're adding a pole to the whole system here. Now, adding a 0 to a setup does make sense. And if you place this 0 a little bit to the left, it makes even more sense because it will attract at least 1 pole or even 2 poles because of the symmetry to itself. And that's a good thing because then they will tend to stay around this vicinity, around this area. But if you're adding a pole to the setup, then you're making everything worse because the stability definition is that if any of the poles passes through the j omega axis, if just any one of them passes, then we're in danger. So you're adding kind of one more to the already problematic situation where we have 2 poles to keep on the left half plane. Now we have to keep 3 of them on the left half plane in order to not get marginal stability or even instability. So that it's becoming harder. And you would see that the asymptotes also become a bit more problematic because we had 90 degrees. Now we have a more less steeper asymptote, which looks with 60 degrees and negative 60 degrees. We were not able, for example, to mess up the stability with this here, but in a moment we'll see that we can mess this up with the PI controller. So yeah, adding a pole at the origin is very dangerous in terms of stability, but it has also an upside to it because we'll see that at the end of the day, it is necessary to have reference tracking. So since we've defined the structure of it, let me just go through the design process here, which is exactly this one here. But here the problem is going to be the fact that we need to add another pole to the system in the closed loop because the order of the system has gone up by 1. So I define a pole, which is going to be real, hopefully. And this is the raise the pole, S plus P. Now we need to update our problem. And hope that it will just solve our issue. Now we can see, first of all, now we have 4 equations. Our closed loop is a third order closed loop because, well, we added another pole. But we can see that magically we have 4k times z in the numerator, 4kz, and also 4kz in the denominator. Now this ratio has become 1. So when I apply a certain input to this closed loop, if it's stable, it will be tracking its input. And this is called reference tracking. So therefore, I'm already at a good place when I come up with a stable design. And the power of this comes from the fact that we are adding a pole at the origin to the system in the open loop. So basically, when I have defined my controller like this will become like the following. I will have S plus Z divided by S, and then also the open loop system. This is going to be the feed forward path. if we have a pure integrator in the feed-forward path, that will correspond to a type 1 system, or that will construct a type 1 system. And type 1 systems can track references of type step inputs. If you add one more, then you will be able to track ramp type inputs. If you add another one, then you would be able to track parabolic inputs, and it goes on like that. But this is a bit extreme to have S cube at the origin, because it's quite hard to stabilize that. But well, we have divided by S, which is placing just one pole at the origin, a pure integrator, and this will then cause the system to track its reference. Now, let us continue on designing our controller. Look at the solution, and we have just a solution here. But unfortunately, MATLAB didn't come up with a good one, because, well, Z is equal to 0. If that's the case, then when we look at this, this will become 0, S divided by S will vanish, and then we will end up in a p-type controller, which is nothing like what we want. What we can do, instead of letting MATLAB to decide on the controller, I could just assign a certain value to Z, just for the sake of demonstrating this. And let's choose Z equals 4, for example. And I've claimed already at the beginning of this day's discussion that this is no way the best way of designing controllers. We should optimize stuff, but I'm just showing you the basic concept of the controllers. So if I do it like that, now Z will be predetermined, and the solution here is a unique one and hopefully a stable one, so I can just use that. So let me look through the solution here. We have p-val, that should be p. I'm not sure that this should cause a problem. K-val, p-val, omega n-val. So everything seems to be in order. So let me get rid of this part here. This is going to be figure 3, and uncomment this. We don't need any color, any for loop. There we go. Now, of course, I need to add the integrator. So 1 and 0 is going to be the S term here. And yeah. Do we have anything else? Well, we're going to add this here and here. Let's get rid of the color, because that's not going to be important anymore. So let's give it another color, maybe blue. Yeah, that should be it, I guess. Yeah. Now let's run our script. Of course, we did mess up stuff. Maybe it's just k-val, because there's no I. Z-val. Of course, here too. Because that's not called Z-val anymore, or we should just call it Z in order to get rid of the problem. And yeah, there we go. Now let's focus on the PI controller. First of all, we can see that we've banded the root locus plots way more differently than we did it before. And yeah, we have a pole at the origin. Where's our cursor? We have a pole at the origin, and we had 2 poles here. So one is tending to the pole at the origin, they coincide, then we have this nice branches here. You can see that they kind of are close to the j omega axis. So in terms of marginal stability, we are at least in the vicinity of j omega. A little parameter change in the system model would cause, or could cause, basically instability. So we're in a dangerous area, but we're working here in a safe zone. a little bit more safer than this here. And you can also see that the 90 degrees and negative 90 degrees for the asymptotes still are there because we didn't change the number difference of the number of poles and zeros, because we added one pole and 1 0 exactly. So the difference doesn't change. So we end up in 90 and negative 90 degrees asymptotes. We again have an omega n value, 1.14, which is a bit lower than the previous one, previous designs, I guess. And then we have the theta line. We see that these two here are, in fact, we are in a good shape because these look to be dominant, at least with a certain ratio, because the extra pole and the 0 of the controller are on the left of our desired poles. So maybe not the best setup, but it seems like we're in a good shape. And we can see that 9.29 is the overshoot value, whereas the settling time value seems to be 5.36 seconds. We didn't really decide on the settling time, so that's not that big of a deal. We could basically, but we didn't. And you can see the effect of the integrator in the feed-forward path that does its job because we have reference tracking. And this one is way more different than coming up with a coefficient for the p-type controller in order to solve that. Because if we apply a certain disturbance, or if we have noise, this will somehow recover. The integrator will cause the system to reach the equilibrium point, which is going to be the reference itself. But this is not capable of doing it because you're introducing an open loop strategy to overcome the problem that the controller doesn't contribute. So the difference of a closed loop system to have reference tracking and a minor adjustment with a coefficient is huge in this case, because this is forced by the controller itself, whereas here you're just adjusting stuff based on some knowledge. But if you have something that you didn't take into account, then the controller doesn't contribute, your method will not contribute, and this will mess up in terms of reference tracking. Whereas here, the system type is increased 1 in the feed-forward path, and you're good to go. You can just rely on that, because theoretically you can prove that this will always track its reference no matter what happens. Unless stability is, of course, violated, you should be ending up in a stable design. You can see that by adding this pole, we just forced maybe a slower solution because we don't really want to bend stuff towards the right. But with a 0 and with this pole going here, we are still okay with this in terms of root locus. Now, again, if we would have designed this using the algebraic method according to or properly, we wouldn't define this in terms of zeros and poles. We would like to have KP and KI or KP and KD because we are looking at polynomials, and the more linearity we introduce to the polynomials, the better it would be. Now, you might ask yourself what a PID controller is, and let me show you what a PID controller would look like, and you can maybe experiment with this on your own. I would just do the same here, but instead of adding 1 0, I would add another one, and that's basically it. And this is the worst way of defining a PID controller in terms of the algebraic method, because now I'm adding 2 zeros, 1 gain, and 1 pole at the origin. But Z1 and Z2, if I'm going to define them as symbolic variables, are not restricted to be real. They can be complex conjugate values or real values. There are 2, or they could coincide. So 3 cases, because this is basically a signorel polynomial. So it could be real distinct, real coinciding, and so real coinciding, or they could be complex conjugates. So this is the case for a signorel polynomial. And in fact, I could just write this down as a signorel polynomial. So I could write this down like S square, actually KD times S square plus KP times S plus KI. This is an arbitrary signorel polynomial with which corresponds to the same like this. So instead of using this notation, which favors the root-Lucas method, because I can see which zero or which zeros are added to the system, and then which gain is chosen, I would rather have this notation for the algebraic methods, because here KD, KP, and KI are going to be real. So sims KD, KP, KI are going to be real because those are the coefficients of a polynomial. It doesn't matter what they are. They can stay real because the solution can still cover complex conjugate zeros or coinciding zeros or real zeros or whatever. But if you do something like this, you're messing up, or you're solving not the whole problem, but a subset of the actual problem, because that's not the only case that can happen. Z1 and Z2 can be conjugates. Therefore, when you're using the algebraic method for PID controllers, for PI controllers, for PD controllers, always go with this KD, KP, KI coefficient scheme, where you are defining it like a polynomial divided into another polynomial that depend on the parameters linearly. If you don't do that, if you do it like this, you will end up in more trouble than you would like to have yourself in. And this also goes for your residue polynomial, because if you want to define a residue polynomial that looks like S plus P1, S plus P2, then the same goes for this polynomial, because they could be complex conjugate pairs, they could be both real and the same, or they could be real distinct. And we don't really want to mess with that. We don't really want to have sims P1 and P2, and we don't want to have complex numbers here. Instead of doing that, just go ahead and use S squared plus A times S plus B as a residue polynomial, because this is depending on the unknowns linearly, and this is a polynomial instead of the poles or the zeros themselves. So if you use this in conjunction with other polynomials, if you multiply and sum them, you will get still linear stuff. And equating linear stuff to each other makes more sense if you are using pen and paper. And even in MATLAB, it makes it more possible to have better solutions. Now, you might ask yourself how this is forming the PID controller. You could see that dividing by S, we get Ki divided by S, Kp times S is going to be Kp, and one of this S square S is going to vanish. So we will have Kd times S, which is derivative. So Kd times the derivative dE dt. And then we will have Kp on its own times E. And then we will have Ki times E times 1 over S, which is going to be another signal. Let's call it Q, where Q is going to be the integral of E dt. So basically, this is going to be the PID controller. And using the algebraic method, we are going to use this notation. But you could actually see from both K times S plus Z1 and S plus Z2, or this approach, you could see that actually a PID controller can be split into KD, let's say KP1, and then plus KP2, so that you have this term here, which is a PD controller, and this term here, which is a PI controller. So you could have PD and PI in series, and that would correspond to a PID controller too. Or you could just have, by the way, we have divided by S here, you could just have this portion to be the PI controller and this to be the PD controller. You might introduce another gain here, K2 and a K1. Then you could see that multiplying K1, S plus Z1, and K2 and S plus Z2 divided by S, which is the PI portion, which is the PD portion, gives you the PID controller. So a PID controller consists of 2 zeros and 1 pole at the origin. And you can see that the potential here is to create more attraction on the left half domain with the zeros, with a complex conjugate pair or real distinct zeros. And the added pole is going to be hopefully on the left half plane in the closed loop, so that we have a stable closed loop system. Now, next week will be about the PID controller design, and we will start designing controllers more optimally or more properly. Here in the PDF, you will see the steps, the necessary steps, and of course, the same results here. We have a certain zeta line, a certain omega n, circle or radius that creates this solution for the p-type controller, where we have 10% overshoot and a certain settling time, which should be theoretically equal to 2, but is less than that because of the modeling performance of our settling time formula. We introduced a 0, and with that introduction, we end up in a more generalized problem, which has infinite amount of solutions, but we just pick random 3 of them and look at what happens. We can see that on the root locus plot, we end up in choosing this point, or there's another intersection, which is going to be this solution here, or we have a negative root locus one, which doesn't really suit our needs, which is too high in terms of overshoot. Then we transition into the PI controller. We add a pole at the origin and a PD controller sort of. And that increases the order of the closed loop system. We have to introduce another pole, residue pole. But then again, we're okay with that because reference tracking is ensured, and we end up in just one solution that tracks the reference and has the overshoot that we are looking for. Of course, I guess this root locus doesn't seem to be the right one. That should be looking differently. Here, a comparison of the resulting controllers is given. And that's basically it for this week. As I've said before, from next week on, we will be designing controllers in a bit more depth and detail. But this was meant to be an introduction to the controller structures, the philosophy of the controllers. Yeah, that's basically it for this week. Now, if you have any questions, feel free to ask. Other than that, we'll
Hocam
see
benim var.
next week. Evet.
Hocam controller'ın somut karşılığı ne? Yani bir cihaz mı?
Şimdi kontrolörün karşılığını en basit anlamda op-amp devresinden, analog elektronikten alıp günümüzde dijital bir yazılıma, hatta bir server soketine kadar düşünebilirsin. Çünkü kontrolör genellikle bir kontrol board veya elektronik board olarak karşımıza çıkıyor. Ama artık günümüzde çok daha geniş bir kapsama sahip. Ama en basitinden şey diye düşünebilirsin. Sensör kartları olup ölçüm alan, ölçümler üzerine bir algoritmayı dijital veya analog gerçekleyip tekrar aktüatör veya işte o sistemin kontrol girişinin birimi neyse o şeyden bir aktüatör olarak düşünebilirsin. O aradaki tüm yapıya biz kontrolör diyoruz. Tabii bizim burada anlattığımız klasik kontrolör olduğu için daha çok şey düşünebilirsin. Sinyal ölçüyoruz. Biz bu sinyali analog ölçüyorsak op-amp devreleriyle mesela türev alıcı, integral alıcı ve işte buffer'lı ve yükseltici devrelerle P, I, D'lere karşılık gelecek. Bunlarla bir seri bağlantı yapıp analog kontrol işareti oluşturuyoruz olarak düşünebilirsin bir tarafta. Bu tabii biraz fazla eski bir bakış açısı. Bugünlerde şey olarak düşünebilirsin. İşte bir Raspberry Pi veya herhangi bir embedded board'u alıp sensörlerle donatıyorsun. GPIO'dan okuyorsun. Yazılımında kontrol algoritmanı gerçekliyorsun. Yazılımın çıkışı tekrar işte DAC'la dönüşüp işte aktüatörüne gidiyor. Mesela motorsa motor kontrol board'u motora dair bir şey ölçüp motorun tekrar akımını kontrol ediyor. Bu aradaki devrede kontrolör kartını koymuş oluyorsun. Bir işte elektrikli araç için yine aynı şey. Hız ölçerin var. Belki GPS'ten ölçüyor. Artık biraz kavramlarla genişlediği için sensör kavramı da genişledi. Yani GPS'ten aldığın ölçümle feedbacklediğin gaz pedalının açısını, gaz kelebeğinin açısını ayarladığın benzin motorlu bir aracı da kontrol ediyor olabilirsin. Burada birimler önemli. Ölçümlediğin şey ne? Çıkış ne? Birim olarak. Ve sistemin girişinin birimine o sana fiziksel olarak nereden ölçtüğünü ve nereden uyguladığını söyleyecektir. Biz tabii burada şimdi haftalardır daha çok matematiksel yaklaşıyoruz. O sebepten biraz havada kalmış olabilir.
Evet, o yüzden zaten hani diyorum bunu yapıyoruz ama ne yani? Neye denk geliyor?
Evet.
Bir de
En basitinden
o
bir motor modeli düşünebilirsin. Tork akım ilişkisinin olduğunu düşün. Akım giriyor, omega çıkıyor olarak düşünebilirsin, açısal hız. Hadi biz ona R de bir teker takıp yarı çapla geri kalan kayıpları da yok edelim. Bir akım borduyla, akımla excite ettiğimiz, yani sürdüğümüz bir motorun çıkışında çizgisel hız dönme hareketinin çizgisel hıza dönüştüğünü düşün. Kontrolör o akımı nasıl üreteceğini oluşturacak ama hıza bakacak. Referans takibi de mesela 25 metre saniyeye çık diyecek. 25 metre saniye hıza veya 72 kilometre saat hıza, o tarz değerlere çıkacağımızı düşünelim. Aradaki farkın hata olduğunu göreceğiz. Zamanla bu hatayı ölçecek. Hız hatasının türevi, hız hatasının integralini zaman üzerinden 3 farklı yerde hesaplayacaksın. P, I değerlerini atayıp, çarpıp, toplayıp akım olarak uygulayacaksın sisteme.
Tamamen mekanik bir sistem olarak düşünsek, kontrolörde böyle ekstra bir buraya da bir şu kadar kilitlilik bir çuval bağlayalımdan ibaret mi oluyor?
H tipi
Kontrolör.
kontrolü için demek kolay tabii ki. Mekanik türev alıcı bir devre varsa ve mekanik integral almaya karşı, yani türev alıcı belki vardır diferansiyel anlamında ama şey var mı integral toplayıcı gibi onu bilemiyorum. O anlamda P tipi kontrolör için sadece denebilir. Belli bir oraya mesela yay takıp mekanik bir sistemde o yayın katsayısı kontrol katsayısı olacak şekilde takabilirsin, evet. O zaman olmuş olur.
Tamam hocam, çok teşekkür ederim.
Rica ederim.